Great.
Thank you for coming, Declan.
Okay, good. Thank you very much, and thank you all for coming along this afternoon. So my presentation is called Climate Change, Water Security and Climate Change. And as Sam has described a bit of my background, I'm actually a geographer. So I do a little bit of everything, and I think you will see from my presentation that I cover quite a range of different material to try to bring out some of the sort of synthesis and insights from what, in effect, in a way, is some reflections on my 20 years of working on the issues of climate change and water resources. So, what are we going to cover today? I want to talk about, just set the context to the presentation, talk a bit about the interactions between climate change and water resources, and I'm going to use a diagram of the catchment, and I will be returning to that diagram as we go through the presentation to highlight different elements of catchment systems that I want to frame to you. And then I'm going to present an overview of the sort of trajectory of research around climate change, climate impacts and water resources for over the last couple of decades. And I will go back to the early 1980s, and I'm going to look at some benchmark papers that have come out over roughly during each decade to highlight to you some of the elements of continuity and change in the research approaches and also insights coming from that research. And I've called that from impacts to adaptation, and you'll see why as I talk through it. I then want to bring us up to date, and to do that I should talk about the current state of knowledge, and I'm going to refer to the IPCC, the most recent fifth assessment report on water resources. But to do that, I'm also going to track through some of the previous assessments and again highlight their continuity and change. And then coming up to more recent time, I want to highlight to you what I think are some of the areas of developing research in terms of water and climate. The quantity of research has mushroomed in the last 10 or 15 years, and it's going in slightly different directions, so I want to try and capture some of those directions. And I will argue that very subjectively we can identify 4 or 5 areas of research where there is a lot of interesting activity, and those areas are around downscaling, the characterization of uncertainty, and looking at how we deal with uncertainty in relation to making decisions. I will then want to say a little bit about contextual approaches to water resources management and decision making. And then finally, I will highlight some insights from integrated assessments, or some of the approaches used in integrated assessments. And then if I have time, I will finish by highlighting some interesting areas of future directions with that. So as you can see, it's quite an ambitious presentation, and it's particularly ambitious in terms of the temporal dimension of what I want to cover in terms of research and the way that has evolved over time. So that's my catchment diagram. I've taken that from a book by Malin Falkenmark and Johan Rockstrom from 2004, Balancing Water for Humans and Nature. And I'll be returning to this as we go through the presentation to emphasize different elements of what I'm interested in. So to start with then, I wanted to say a little bit about what I mean by water security. I'm not going to be overly focused on definitions and so on, but I thought it would help just to say something about that. I like the widely cited definition that comes from David Gray and Claudia Sadoff's paper in 2007, which is availability of an acceptable quantity and quality of water for health, livelihoods, ecosystems and production, coupled with an acceptable level of water-related risks to people, environment and economies. So we're looking at stability, reliability, both in terms of quantities of water, the quality of water, and in addition to that, we're interested in protection of people from hydrological risks. So that's a good working definition. There have been a number of recent papers which have looked at other definitions and the way definitions of water security have changed over time. Cook and Becker have done some recent work on that, and they've identified really 4 themes that get encapsulated in work on water security. And those themes are around availability, around vulnerability to hazards, around human needs, and that's particularly in relation to access to water for growing food. And then also sustainability. So we have a significant temporal dimension to water security, and perhaps actually maybe in terms of the fifth dimension would be around equity. So when we talk about water security, I think that for many of us, implicitly within that, we would have an understanding of the idea or the objective of including equity in terms of access to water. So those are the sort of working definitions. I think the key point that I want to make with my definition is really in the diagram here, which is our catchment system, and that is that we're looking at a coupled physical and socio-economic political system that provides the canvas for our work on water. So, climate change and water security, what are the main challenges that the climate change represents for water? So within our catchment, we've got inputs and outputs. Global climate change, anthropogenic climate change represents a perturbation to the system through changes in the characteristics of precipitation. So either the state, the timing, the amount, or the intensity of precipitation. In addition, we will see changes in characteristics of timing and quantity of snowmelt and glacial melt, and that's going to feed through into hydrological processes on the land surface. And then as temperatures change, we will see changes in evaporation rates, so the different factors affecting evaporation from the terrestrial surface. Higher temperatures, changes in radiation, changes in humidity and wind speed will interact to change the evaporative demand of the atmosphere in potentially non-linear and quite complex ways, but that is going to be an important dimension of the way hydrological processes and water availability will be affected by climate change in the future. So those are our two big drivers: a change in the inputs, precipitation, change in the outputs, evaporation rates, with spatial and temporal variability in those. They will be moderated, mediated by the effects of climate change on land cover. As temperatures change, as moisture availability changes, we will see natural responses within the catchment land system, which will have a knock-on effect for runoff pathways and for evaporation rates, affecting the end impact on water resources. So the net effect of these interactions will be to produce effects or impacts on surface waters, changes in the volume of river discharges, flows, the timing of river flows, the frequency of extreme events, etc., and also potentially the changes in the rates of groundwater recharge. So these are the elements of change within the physical water resource systems or the hydrological cycle, which we are interested in terms of managing water resources and thinking about how we can achieve water security for current and future generations. And then, of course, in terms of coastal processes, we've got sea level rise, we've got saline intrusion, and so on, but I don't have time really to talk very much about that, but of course that is an important element of climate change and water. So that is the potential perturbation to the system that we are concerned about when we think about climate change. The point that I wanted to make about this, of course, is that the way society has co-evolved around water in terms of the way we use water, the infrastructure that we have to manage and distribute water, the regulations and the institutions which have formed around water, make assumptions about the temporal characteristics of water availability and the spatial characteristics of water availability. And we very much assume, or have assumed, that the system is a stationary system. So over the long term, we don't see major shifts in water availability. We can assume that variability is within a long-term stationary mean. The issue about climate change is that it undermines many of those assumptions, and it undermines many of the methods and approaches that we have to deal with effective management of water resources, and will change the statistical distributions and giving us a non-stationary system that we need to deal with. And this was really captured in 2008 in a paper by Milley and colleagues in Science in the Policy Forum, where they confront us with this challenge that stationarity is dead. Climate change undermines many of the assumptions that we have about managing water resources, and that is the challenge for us as a community, is to think about, well, what are the consequences for the way we approach characterizing uncertainty and statistical distributions and managing the balance between supply and demand and managing exposure to hazards and so on. Okay, so we have a question about stationarity. You may think, you may argue, and I think many of us would, that actually we know that we're not dealing with a stationary system, and many aspects of water resource management have evolved over time to deal with variability, to deal with uncertainty. We know from the historical records that over multi-year, decadal periods, we see changes in the mean characteristics, we see changes in the frequency and magnitude of extreme events and so on. So we have really been managing a slightly non-stationary system. We've had non-stationary behaviour in demand for water resources over the last 100, 150 years since post-industrial revolution. So there are many dimensions of non-stationary behaviour historically which have led to the fact that a lot of our water resources management is really conditioned by dealing with variability. And it may well be that in some cases, well, we already have enough capacity to deal with variability as we move out into the future, depending on the magnitude of climate change as it occurs. So to emphasize that, the fact that we've been dealing with historical variability, I've got a slide here which is a time series of the annual flows of the Nile as it flows into southern Egypt at the Aswan Dam reservoir or upstream of the reservoir. And that record goes back to 1869, and each bar is the annual river flow, and the dark line is the moving average through that. So you pick up from the moving average some of the decadal variability in the river flows. And the point to make here is that prior to 1900, there was a humid period with much wetter conditions in the upper Nile basin, leading to high Nile river flows. In the 1980s and into the 1990s, there were multi-year periods of much drier than the long-term average conditions. So the system has shown quite extreme examples of non-stationary behaviour over time, and the two pictures at the top of the diagram represent a stilling well, a historical stilling well called a Nilometer. It's on the Rhoda Island in the middle of Cairo, and it was constructed in the 8th century, and it's been recording the levels of the high flows and low flows of the Nile ever since then. So we have a good documentary record of the magnitude of those fluctuations over time. So we've got this issue about non-stationarity, that climate change represents a perturbation to that, and a challenge to our capacity and ability to be able to deal with uncertainty and variability in hydrological systems. Okay, so that provides the context to what I'm going to talk about now. I want to step back a little bit and then trace through how have we approached our understanding of the challenge or the problem that climate change represents for water resources management. And to do this, we've got to go back to the early 1980s, and I will show an example of a paper that was published in 1982 by Nemish and Sharkey, two very well-known hydrologists, who talked about the sensitivity of water resource systems to climate variation. Okay, and there is a quote from the paper: the importance of the sensitivity of the systems, water resource systems, to such variations is demonstrated with respect to the stationarity of the mean and the extremes. So they're picking up on this issue about non-stationary behaviour in water resource systems. This is the early 1980s, so they do consider anthropogenic climate change, CO2 forcing or greenhouse gas forced anthropogenic climate change, as one source of non-stationary behaviour. They're also interested back then in, well, still would be solar variability, moving into a new glacial period and so on as drivers, potential drivers of non-stationary behaviour. But 1982 was post some of the first early climate model experiments looking at sensitivity of global temperatures to CO2 increases. So within the literature, you do see quite a lot of interest in what the consequences of that would be for different sectors, such as water resources. And they discuss the difficulties of estimating reliability in hydrological systems because of the inherent dependence on stationary behaviour and the way our management systems and our infrastructure has been designed over time. They look at how variability or non-stationary behaviour may affect hydrological systems by taking a hydrological model of a river basin and perturbing the inputs to that. And in fact, they take hypothetical changes in temperature and rainfall, either a 1 degree, 2 degree increase, or a 5–10% change in the rainfall, an increase or a decrease. And they look at how does that affect the runoff, both in terms of the volume of the runoff and the timing of the runoff. And this is a very widely used approach to try to understand impacts of climate change that I will come back to. So it's a very early example of taking that approach. And the results that they obtain through this methodology are to highlight that there is much greater sensitivity of runoff to precipitation than to evapotranspiration. And they also pick up some interesting contrasts between semi-arid catchments and humid catchments and differences in their sensitivities either to changes in temperature or to precipitation. So that's the early 1980s. If we move forward through that decade, we get to the mid-1980s, and we come to a consolidation of methods. So Peter Glick, and I guess that many of you will be aware of Peter Glick and his work on sort of global water resources and characterizing some of the big challenges that we have in terms of global water. But Peter's early work, in fact from his PhD, was looking at impacts of climate change on water resources in California. And he took the approach from Nemish and Sharkey, which was to take a hydrological model of a river basin system and perturb the inputs to that. And I've taken a quote from his paper, which is that the most profound effect of such climatic changes may be major alterations in regional hydrologic cycles and changes in regional water availability. Unfortunately, these are among the least well understood of impacts. So by the mid-1980s, we're looking at a much clearer focus on anthropogenic climate change as a driver of non-stationary behaviour, and that's quite a significant change during those 4 or 5 years. He looks at a range of different approaches to try to understand the connection between climate and water resources, but he focuses on this idea of using a hydrological model to assess sensitivities and makes a strong argument for a set of advantages to using that kind of approach. And much of that argument is based on the scale issue in relation to global climate models and the coarse scale of information that they provide in terms of climate scenarios being really too coarse to use in terms of decision making around water resources management. So we need to couple them with hydrological models to give us the kind of spatial and temporal scales that might be relevant to decision making. So that's the point there. And the rationale for that is limitations in knowledge of regional scale consequences of climate change. And this paper really is a benchmark publication in a way, because it sets out the approach that many of us have used and many people are still using in terms of trying to quantify and assess what the implications or the impacts of a shift in the climate might be for water resources. But I'm just going to read you another quote from that paper, because he presents in a very valid way that this is a sensible approach to try to characterize climate impacts. But he makes the point about using what I've called here the GCM is a global climate model. So these are the global models which the climate modeling community use to understand the way the climate system will respond to increasing concentrations of greenhouse gases. And those are run out into the future to look at the global heat response to rising concentrations of GHGs, greenhouse gases. And from that, we can pick up what are the spatial patterns of change in temperature and rainfall. And we call these scenarios or projections. And we then use those with hydrological models. So he talks about this as a sensible approach. And he makes the point that while the present quality of the regional information provided by GCMs is considered to be low, Improvements in hydrologic parameterizations and grid resolution of these models over the next several years will improve the quality of regional climate evaluations. So this is back in 1986 with a fairly optimistic picture of the way reliability and accuracy of global climate models would pan out over the next 5-10 years. And we will see as I move through the presentation that actually that hasn't been the case. And in fact, rather than a convergence of predictions in terms of climate, we see quite strong divergence in the detail of the way temperature and particularly rainfall will change. And that has presented us with major challenges in terms of how do we characterize the threat or the risk that climate change represents. Okay, so we moved now from mid-1980s, from Glick's work on methodologies, to a move from an agenda which is very much a research community and a sort of model-based approach to assessing impacts to saying, okay, so we have a problem, or we have a potential problem, we have impacts of climate change on water resource systems. What do we need to do about that? What are the policy, what are the management implications of the kinds of risks or changes that people are predicting could occur? What does that mean for the day-to-day operation of reservoirs or of water utilities and so on? How do we move this from a research to a practice or an applied agenda, if you like? There's a good set of papers in a publication by Kenneth Frederick, which came out in 1997, which was looking at climate change and water resources planning criteria. And the quote that I've taken from that is that up to that point, and this is a very strong point and an important point, that relatively little has been done to review the adequacy of existing water planning principles and evaluation criteria and related impact procedures in the light of potential changes. So we're looking at a research agenda which hasn't really driven a lot of changes in practice or spoken to practice communities. And they address this by looking at this as a first step in terms of assessing whether and how water resources management should be revised in the light of potential impacts of climate change. And they ask a couple of very important questions. So the first one is, does anthropogenic climate change require planning criteria beyond existing capacity to deal with uncertainty and variability? Which goes back to that point that I was making earlier on, that systems have evolved around dealing with variability. Or does, as some have argued, climate change simply represent one more exogenous factor to consider within the whole range of factors of change and influences on uncertainty within water resource systems, and that perhaps we have enough inherent capacity to be able to deal with the sorts of changes that could occur in the future. And to do this, they look at case studies of water resource systems, reservoirs, lake systems, flood early warning systems, to highlight what are the sensitivities of those systems to potential ranges of changes in impacts, and is there enough buffering capacity within the systems to deal with the sorts of changes that are occurring. And in fact, in most of the case studies that they looked at back then, they found that actually there was enough headroom or flexibility in those systems to be able to deal with the broad range of impacts that were being projected through climate scenarios. So that takes us up to the late 1990s. And to characterize the nature of the research then, it was very, very much around a predict then act approach. Okay, so we have a catchment system, we have a hydrological model or a water resource systems management model, a decision support system. We model the system, we perturb the inputs, and we predict the outputs, and we think about then, well, all right, what do we need to do as a consequence of that? And that was very much the paradigm that we were using. And the kinds of outputs of this type of work are characterized here, which is a slide from IPCC from the fourth assessment report, which is actually, I've taken this from the Bates technical report on water, but it's from the fourth assessment report, which looks at future climate change impacts related to fresh water. And it has, as a backdrop, it's got the outputs from a global hydrological model, which has been driven by climate projections from a set of different climate models to tell us, in terms of the colours, what is the change in runoff for this period is the 2090s at the end of the century, with the blues and the purples representing an increase in runoff, and the sort of browns and the dark reds representing a reduction in runoff. And that's the backdrop. And then they highlight individual studies which have looked at what are the impacts or the consequences of these sorts of changes. And I've just highlighted one example here, which is groundwater recharge decreases by more than 70% by the 2050s. And that's the kind of example of an output of an impact-driven type study. Now, there are problems with this type of approach, and I'm going to highlight some of the problems in the next slide, and I'm going to return to this IPCC slide of changes in runoff in a minute as well, because it's got some important other information in it about uncertainties. The problem with many of these impact studies is that they're often very far into the future. So this slide represents the 2080s, 2090s, which is way off the horizon of many decision makers in terms of water resources planning and so on. So they're too far into the future. They often only consider climate. Now, there will be land use change, there will be changing demand, there will be economic growth, there will be migration, there will be new technologies for water reuse, water treatment, etc., which mean that a 30% change in groundwater recharge in the 2090s is almost meaningless information for the way we are currently managing our water resources. So they don't give us much context, which is the next point that I want to make, which is that they don't really address decision-relevant factors very effectively, and that they also fail to capture a lot of uncertainties, and I will come back to the uncertainties point in a minute. And I think that means that a lot of this work has had really a lack of traction with policymakers, with water utilities, and with the management community, or the water resources management community. That has meant that during the 2000s, we have begun to grapple with, well, how do we modify our approaches to understanding the consequences of climate change to make them meet more demand-related objectives from a water management community. I'm going to talk about some of that work in a minute, but before I do that, I just want to very quickly step back a bit and do a little bit more focus on the historical trajectory of the research agenda. And I've looked at from the different IPCC reports. So the first one was 1990, through to the fifth one, 2013, Working Group 1, and Working Group 2, which looks at impacts, was actually last year, 2014. And I've gone through the chapters on water resources in each of those. So every IPCC assessment report has had a chapter on the impacts of climate change on freshwater resources, and it's summarised the state of the art in terms of our understanding and case studies and so on. And those are the chapters and the chapter titles. 5 assessment reports, and then there was a major climate change and water technical paper that came out in 2008 as well, which is quite a useful source of reference for this topic. And the point I wanted to make here is that there is quite significant continuity and change as we track through these successive IPCC reports. And I've got a set of statements on the left which are broadly taken from the reports. I've changed them a little bit, but because they're different from each chapter, but the points are similar across the chapters. And then we've got from the first, second, third, fourth, fifth assessment report, just saying whether the statement is present. And from that you can see that the first 3 statements have been there right from the outset, and they're still there, and the issues they relate to, a lot of the approaches that we're using, have not really changed that much or gone away. So the top one, uncertainties are high. We need more reliable and detailed estimates of future climate conditions, better scenarios, better impacts models. Snowmelt and glacier-fed systems are more sensitive to temperature than precipitation, and in fact actually those are the systems which exhibit most of an anthropogenic climate change signal. If you look at systems which are predominantly rainfall based, then it's much harder to detect any signals from anthropogenic climate change. But the temperature-sensitive ones do show those responses. And then the fact that we've got this difference in humid and semi-arid catchments, and semi-arid catchments tend to have a much higher sensitivity to changes in rainfall than humid systems. But then, as we come down with these later statements, they're not in the early IPCC reports, and these are, well, there's three of them. One is current water management practices are very likely to be inadequate to reduce the negative impacts of climate change. So that's counter to the point that I took from Stakib earlier, which was that systems have enough flexibility within them to deal with climate change, and they're arguing that that isn't the case in the fourth assessment report. And then we begin to see adaptation procedures are being developed in some countries. So this is particularly in the UK, in the US, and in Australia, where water utilities or government agencies for water management are beginning to include climate risks and adaptation within their operational management activities. And then finally, interestingly, in the fifth assessment report, we've got this new point that mitigation policy represents a challenge risk to water resources management. So there are dimensions of a mitigation agenda that are going to have knock-on effects within catchments that may have implications for water resources management. So those include things like afforestation policies affecting runoff processes and evaporation, biofuels, and whether biofuels development requires additional irrigation water, water for irrigation, and so on. So we may see consequences of mitigation policy playing out in terms of water resources. So to bring us up to date then, life gets much more complicated. I've been able to, up to this point, to just pinpoint what I think are some of the benchmark papers over sort of 5 to 10 years. When we get to the 2000s, life is much harder. And that's characterized here by a very simple word search in Scopus, where we've looked at two word strings: climate change water impacts in the grey bars and climate change water adaptation in the black bars, going back to the going back to 1990 up to late 2012. And it's just simply the count, the number of papers that have those words in the title, I think it is. And you see from that that impacts research starts earlier, and there is much more impacts research up to the point where at the present we're looking at well over 1,000 papers a year on this topic. In terms of adaptation, or papers with adaptation in the title, with water, we've got far fewer, and they really only appear in the mid to late 1990s, and we're looking at probably about a third of the volume of work on that, but quite significant increase over the last couple of years. The point that I want to make about that is that there is this lag between impacts and adaptation in the literature, and this occurs in other sectors. If you look at agriculture and so on, you see a similar thing. But it's easy to describe the research back here, but it's much harder to describe this volume of research because there are so many papers, but I'm going to attempt to do that anyway, all right? So divergent directions, okay, we've got over 1,000 papers a year coming out on this. I think that broadly, in a very qualitative sense, there are sort of 5 main themes here. There are some sub-themes that one might argue about, but I think these capture a lot of them, and some papers cross over between the themes. So we've got scenario development, and that's very much a downscaling agenda, which is about trying to relate the large-scale patterns of change in temperature and precipitation from a global climate model to local changes in precipitation and rainfall. And there are many approaches to do that. Characterizing uncertainty. Okay, so we recognize that actually, unlike what we thought would happen back in the 80s, that we would get a convergence in terms of climate model projections, that hasn't happened. We get divergence in many parts of the world, and therefore uncertainty is a big component of how we get to grips with what we need to do about climate change from a practical perspective. And people are looking at multiple probabilistic climate scenarios, And interestingly, they are also now beginning to recognise the importance of hydrological model uncertainty. The fact that the different hydrological models can have very different sensitivities to the same climate perturbations. So we need to factor that into the way we begin to characterise future impacts. So we've got model parameterisation, very important. We've also got a lot of uncertainty about future drivers in catchments like demand and so on. Okay, and then we've got this third area, which is flipping the problem around and saying, all right, we know there's uncertainty. What are the consequences of the uncertainty for decision making? So we've got ideas about how do we approach decision making under conditions of high levels of uncertainty. And this is around ideas of robustness, flexibility, adaptive management, and so on. And we've got this fourth area, which is a more qualitative approach, which is about understanding the existing management context within catchments to then map that against what some of the future risks might be to understand how significant those risks might be for existing operational considerations within catchment systems. Those rely very much on case study reviews of management, active perspectives and capacity assessments. And then fifth, there's probably fewer of these, but integrated studies where people are beginning to try to model and assess all the changes happening in catchments, population growth, changes in demand, changes in land use, etc., urbanisation, and looking at climate change in the context of those other drivers of change. So I'm just conscious of time, so I'm not going to spend long on this. Downscaling, I've already explained to you what that is. That's about this producing more detailed information from climate models. There are a lot of different approaches, weather generators, regional climate models, and so on. Characterizing uncertainty. Well, uncertainty is a big feature of what we're trying to do now and what we're getting to grips with in terms of climate change and water security. We're fixated on uncertainties because they're very large, okay, and there are a lot of sources of uncertainty. So in the climate world, people will often characterize this cascade of uncertainty, and you may well be familiar with this, which is that we don't know what the greenhouse gas emissions will be like in the future. We don't know exactly how that will convert into concentrations of greenhouse gases. We don't know exactly what the implications of that will be for global temperature, the climate sensitivity, and importantly, we don't know what changes in global temperature will mean for local changes in temperature, evaporation rates, precipitation, and so on, the kind of information that we're interested in if we want to understand what the risks are for our management activities. And the issues there are about spatial and temporal problems, but particularly relating to many water resource systems or hydrological situations, and that precipitation is fundamentally important to the system. And the models produce divergent scenarios of precipitation, so that's a big problem. And then now we're also interested in the step from climate scenarios to hydrological impacts, because we recognize that different hydrological models have different sensitivities. So I'm going to say a little bit about those two steps in this cascade of uncertainty, because they are very much where a lot of the research is focused. So go back to this IPCC slide. It's showing us the change in runoff, surface runoff percent change for the 2090s. The coloured areas are where we get decreases or where we get increases. The white areas are areas where there is strong disagreement between different climate models. Okay, so this is where, if they use a sample of, say, 10 climate models, over half of those, less than half of those models are in agreement about the direction of change of precipitation. In fact, it's less than 2/3 of the models are in agreement. So the white areas are parts of the world where climate models are suggesting it's going to get both wetter and drier. So we have very high uncertainties about the nature of the direction of change in terms of water resources. And that's a fundamental consideration when it comes to looking at what are the practical considerations of impacts. This is from the 4th assessment report. This is in the 5th assessment report. and it comes from a paper from Shui and many other authors, and it is the collection of taking global hydrological models. I think they use 7 or 8 different global hydrological models, and they force those with climate scenarios from 15 or 16 different climate models, all the climate models that go into the 5th assessment report. And in effect, it's a very similar plot to that one, but the key difference is that it's using more recent climate model scenarios, but it's also using more than one hydrological model, okay? So this one is just based on one hydrological model, and this one is based on the average of 7 or 8 different hydrological models. And down here is a similar scale to the previous slide. It's slightly more complex, but in effect, the white areas are the areas where there is large disagreement about the direction of change in terms of precipitation in the future. The really interesting aspect of this work and the novelty of it is that they look at the uncertainty that relates to the differences between the climate model scenarios and the differences between the hydrological models, and they present that as a ratio, which is the ratio of GCM, climate model variance, to total variance. So in red areas, the variance is related to the global hydrological model, all right? So that is our understanding of the runoff processes, and the sensitivities of the models are very different in these areas, whereas the areas in blue represent areas where the uncertainty is mainly a function of the climate scenarios. So that the interesting areas here, these areas in red that come out, and that a lot of these are the semi-arid systems where the hydrological model response is quite different to the same climate perturbation. So we now have uncertainty related to climate scenarios and another layer of uncertainty related to hydrological model sensitivity. So that's a big step forward in terms of our understanding of uncertainty. It creates another problem for us in terms of management implications. So that's characterizing uncertainty. We then flip the problem on its head, and we come at this by saying, we know there's a lot of uncertainty, and we've made decisions under high levels of uncertainty historically, and we will continue to do so in the future. What we want to do is to make more effective decisions given the uncertainties. So we accept that the perturbations in precipitation and evaporation are going to be very difficult to characterize, and we will be looking at a range of distributions of those in terms of our future climate conditions. We're also probably going to be looking at a range of conditions in terms of land cover, land use, rates of urbanization. So we have a probabilistic description of future catchment conditions and what that means for distributions of hydrological flows, discharges, intensity, magnitude of extreme events, and so on. And we look at, we accept the uncertainties are large. What we want to do is identify situations where we can deal with those uncertainties and identify decision pathways which are less sensitive to the uncertainties, so that might work well across a range of future outcomes in terms of flood risk, in terms of water availability. So we've got robust decisions defined as decisions that would work well even with the inclusion of various uncertainties. So we're not optimizing for individual response pathways. We're looking at multiple objective functions where we're trying to capture the uncertainties and find a path through those uncertainties that works well across a range of potential outcomes. And then fourth, how am I doing for time? Not too bad. Context. So this is another, again in a way, it's sort of flipping the problem around, and it's coming at it by looking at what's the existing capacity, the way that water resources are managed, which institutions, which actors are involved, how is water supplied, how do people access it, what is the regulatory and policy environment, and understanding that, and understanding what's important in terms of the role of climate. How does variability, changes in water availability, flood events, how does society and institutions, organizations deal with those sorts of events? So the sorts of things that people will study here are looking at historical management, how have we dealt with extreme events, what's worked well, what's not worked so well. Institutions, what's the capacity of institutions to manage water effectively, to try to preempt or anticipate changes in water availability. We're interested in supply-demand balances, who are the users, what's the allocation regimes across different users. We're interested in key recent trends, urbanisation, population growth. Critically important, the legal and regulatory frameworks that we're operating within, and how do those interact with variability, and how might they be effective in terms of change in the future. What's the decision context? How important is understanding uncertainty if we know that the political economy of decision making is such that infrastructure investments are going to go ahead anyway, whatever we say in terms of the technical considerations of those. Is there a lot of point in us going down a downscaling route if that type of information is not really going to be relevant to the core of the decision making process? And we're, alongside climate, we're interested in key future drivers. So there's a whole bunch of studies that take these sorts of approaches. Some of them are motivated by climate change, but many of them are actually just motivated by understanding water management systems in their own right. And they have a lot of rich observations and detail, which are important for us to take from the climate change community to accept the fact that, you know, we're managing water under many changing conditions, and that climate change is just one of them, and in many cases may not be the overriding driver of policy change or infrastructure investments or whatever it may be. There's a lot of different types of approaches there. So, integrated assessments, I mentioned there, integrated modelling approaches where we're trying to factor in more variables that are changing in the future in addition to climate change, and there's quite a few examples of those. A lot of examples now coming out of global studies and some sort of catchment level studies. Where are we going now? So the 2010s, I've made this argument that we've got these 5 areas of research. What do I think are interesting areas that we will continue to look at, or perhaps look at in a bit more detail? Well, I think that uncertainty in this remains high and is likely to continue to dominate adaptation responses. And an issue here is that, you know, we have a strong, almost a supply-driven agenda that society is being asked or expected to adapt to climate change in the future, and yet we are at a stage where we don't really have effective methods and approaches to plan for that adaptation because of the very high levels of uncertainty. So that puts us in quite a difficult position. And I think some areas for research will be very much around this uncertainty about hydrological model response and the fact that different models give different sensitivities and response functions. And a key one there is the direct effects of CO2 on water use, transpiration rates, or water use efficiencies. And that some hydrological models have those processes in them, many don't. And this is just a slide from a global study comparing hydrological models with and without CO2 direct effect functions in them. And the coloured dots down here are models that do include them, and these models don't. And we see, you know, a huge divergence in terms of model response. So critically important to get a better understanding of those processes. Mainstreaming adaptation. I've not given many examples of this, but the UK, our water utilities, now has approaches to factor climate risks into their water resource plans. So the sector is doing this. We are now adapting, and it is informing the way organisations are working. And we have legal policy frameworks requiring water organisations to factor climate risks into their plans in the UK and a couple of other countries. And that's very likely to be the entry point and the way other countries will adopt adaptation processes in their water management, I suspect, through a regulatory framework or driver. This issue of multiple stresses and drivers of change in catchments is very important, and I think is being more widely characterised now around this nexus of water, food and energy, and it's probably likely that we will see far fewer studies just focusing on climate change as a driver, but we'll be looking at a whole range of different drivers of change within catchments. And then the last point is around weather and extremes, which and I'll elaborate on that in my final slide, because I'm due to finish. So, which is back to the catchment and back to our definition of water security. And here we've got the first part of the definition, which is availability of an acceptable quantity and quality of water for health, livelihoods, ecosystems and production. Now I think here that in terms of what are the drivers there and what are the concerns about quality and quantity, well, they're actually very likely to be the multiple stressors: population growth, urbanisation, economic development and land use change within basins, certainly out to the 2050s, and a lot of integrated studies that look at this. The big drivers really are population growth and per capita change in water use. If you go beyond the 2050s, global population stabilises, economic growth stabilises in many developing regions, and then climate change begins to have a much bigger effect. But up to the 2050s, that is the case. If we look at risk then and hazard, an acceptable level of water-related risk to people, environments and economies, well, I think this is where climate change comes in the more near future. And it's the tails, the low flows and the high flows, and the way climate variability is interacting with anthropogenic climate change, and it is changing those tails and the characteristics of those tails. That is where we will get hit by climate change in the near future, and that is probably where we need to be focusing a lot of our effort in terms of trying to characterise the risk and also thinking about the way we respond to that. Now, there are multiple stresses there, land use change and so on, but I think that climate change will be a key dimension of that. So on that note, I will finish. Thank you. Yeah.
As far as rather than, in the very long term, right out to 2100 sort of thing. How does your analysis deal with a case like that?
I suppose where I would go there would be to the recent work which is aimed at trying to understand those process interactions. What is happening in those snowpack situations? What do we know about precipitation change? How is that changing? What do we know about temperature change? But what do we also know about radiation changes, which are also going to be very important in those snowmelt processes? And can we disentangle the interactions of those processes to understand what's happening to the flow regimes downstream? So you've got a better biophysical understanding of the recent variability, and then you can modify your hydrological models to incorporate that improvement in understanding. And then you can look at, well, what has been happening in terms of water management in California? Who has been responding? How have they been responding? And how might one improve that response in terms of looking at water markets or reallocation or contingency plans for low flows and those types of things. So it will be looking at the recent past and trying to draw both physical insights and social insights from understanding the processes of change. A lot of policymakers and decision makers will rightly be asking the question, what is this? Is this just variability? Is it a decadal variability that we're moving through this very dry period, or is this anthropogenic climate change? And can we make any confident statements about that? And I suspect that given the historical variability of the system, we may not be outside what has been experienced over the last century or so to be able to say that there is an anthropogenic element to what is happening. But I don't know the system that well, so I'm speculating there. You could argue that the temperature rise in those areas is well outside what we've observed historically, and that the effect of that on the melt processes is an anthropogenic effect in the systems. So they are reflecting some kind of anthropogenic climate change. I don't know that that is a problem in a way. I think I would say that if the uncertainties are that large and there are other perhaps more quantifiable pressures on the systems, you take a wait and see approach. So adaptation can include let's wait and see what directions of change occur over the next 5 or 10 years, and then we begin to plan for what may happen. So and I think that is a perfectly valid response to a situation where we do have high levels of uncertainty in it. So I might, I'm not arguing against adaptation, but I'm saying that adaptation can include low regrets type measures. Yeah.
The later one. I mean, if you look at Spain in the context of Europe, it looked as if it had some pretty nasty precipitation problems.
Yeah.
Does it have a historic? It probably does have some historic problems in relation to that. But can you flesh that out at all, just from a geographical description of what's going on there?
I think that again, I don't want to not answer the question, but I would say you look at the existing water supply demand issues in Spain, and it's very likely that they will be exacerbated in the future. Most of the climate models suggest it's going to get drier in the region. High evaporation rates are already a problem in terms of water availability and irrigation and so on. They're likely to increase, other things being equal. So water availability is going to be a critical issue. And looking at how you allocate water between different users and so on, and the mechanisms that you have to do that, you should be looking at those mechanisms and seeing where are the current problems with them, and are we using water effectively at the moment from a set of different criteria that we might have to value what is effective. And on the basis of that, begin to say, well, the crunch is on, the evidence suggests it's going to get drier, we need to improve these existing management systems for dealing with that. But that slide throws up a really interesting problem in that if we have strong agreement about the climate models and the direction of change, is that a valid enough set of evidence to influence investments about infrastructure? The previous questioner gave an example where Ofwat, the UK regulator, has told the water utilities that at the moment, because of the very large uncertainties, you can't justify passing on investment costs to consumers just on the basis of preparing for climate change in the future. You need another rationale to justify your infrastructure investments. Now in Spain, how could you argue that all the models are saying it's getting much drier, and therefore you would promote, well, whatever, what are the responses, a mix of infrastructure, a mix of soft water demand management approaches? Well, perhaps you would be a bit more confident about doing that. But that's assuming that the climate models are in agreement for the right reasons. It may well be that they're in agreement for the wrong reasons, that they don't capture the Mediterranean climate processes as well as they should do.
The reverse will be possible. I mean, I guess because, for example, in Spain's case, they're considering this building desalination power plants which consume fuel. So in this case, scarcity.
Yes.
Additional stress to climate change.
Yeah, that's a good point. That's a good point, and it is in the last two chapters, the last two reports in IPCC, but it's not really given much attention. And I've done quite a lot of work on energy use in the water sector, and it's quite an energy-intensive sector. And a lot of adaptations may well be very energy-intensive. So, for example, desalination, pumping groundwater, and so on. So you've got to factor sustainability and emissions into your adaptation response strategy critically. I think a lot of the companies they're being required by the government to report their emissions and what they are, and their operational costs are, well, they're not dominated, but a lot of those costs are related to energy costs, so they're looking at trying to bring down those and bring down their emissions, but it's very important.
Shall we take a discussion with maybe Mr. Quay?
Yeah, okay, great.
What the world to sustain and enjoy. Glad you joined me. Thank Professor Declan Conway. Thank you.
Thanks, Sam.